All right, I want to talk about functions. Now, functions can be written, or we write functions in different formats. What I'm going to do here is use some subscripts to denote that I could have multiple variables. And this is a multivariate function. The function that we're used to seeing is f of x, normally said, or a single variate function. Now, what happens is the numbers that are pulled from the domain for these variables pass through a rule, and that rule is the function, and it returns a value. And in this case, x draws from a domain and passes a value back to the function f. And so, since we are mainly going to focus on single variable functions, I will be talking about this format of these. And so what we want to kind of look at is to define some terms. F is the dependent variable. And x is the independent variable. And our definitions of dependencies talk about how we draw values. We tend to think of the independent variable is allowed to grab any value from its domain. And that value filters through the rule that is the function and spits out a thing called a range. And so we're going to try to look at this. So the independent variable, now in this case, is x. It doesn't have to be x. I could write some function of t, or I could write another function g of y if I wanted to. This in the parentheses is the independent variable, and the function name on the outside is the dependent variable. And we can think of it as the value of the function depends on the independent variable that I put in. So x, or the independent variable, and you'll see we'll tend to say f of x a lot, unless we have specific models we are using. And so the independent variable is taken from a set of numbers called the domain. Right? And we're going to call our domain D. And that is a set of numbers from which the independent variable is drawn. Independent variable is drawn. We try to use the widest set possible when choosing our domains, which will usually be the set of real numbers. But we will spend some time working on what it means to have restrictions on the domain, or we can choose from complex numbers as we move on, right? Numbers that are real and have imaginary numbers. But most of what we're going to work with are real numbers and the functions of real number values. Now, as I pull an x value through, the rule of the function spits out or returns a value. And so the return value we're going to call the set E. And so this is the domain. It's the set of values that the independent variable can be drawn from. And then we're going to look at a value called the range, E, which is the set of numbers generated by a function. And so we have kind of some placeholders to give an idea of what a function is, and then we'll look at some different meanings we can associate with it. So having a domain and a range being a set of numbers, without specifying any particular set, we can say that the definition of a function, f is a rule that assigns to each element x in set D exactly one element called f of x in set E. And so there are some visualizations to look at what happens. The first method is usually we think of a function as like a black box machine. And you have the rule f, and some value of x goes in, and spitting out is f of x. And the rule tells you how to process the quantity that comes in and to put out a value. Now notice only one value comes out. One value goes in, one value comes out. Another way this is sometimes looked at is mapping, and you could make a area that represents all the values in the set of D, and an area that represents all the values in the set of E. And the functional rule takes x and maps it over to f of x. Now there can only be one line leaving each x, so I'll call this x sub 1. But functions can end up at the same value. So x1, the rule can generate a value f of x. x2 could generate the exact same value, but x2 only ends up at one value. x1 only ends up at one value, and that's the exactly one element part of defining a function. And the other way, and the way that we will most likely look at functions often, is to turn these into graphs, where some value of x generates an output in y. Now, for only one value of x, if this is my x-axis and this is my f of x-axis, and we have a tendency to say y equals f of x when thinking of graphing, to get the exactly one part of it out, it generates what's called the vertical line test. If I look at any value of x, oops, let me make a proper vertical line here. If I look at any individual value of x, and I extend a vertical line, it can only touch the function at one point. One and only one point. There cannot be more than one point. And let me highlight that point here. And so this curve is a function. And it is a function that has some rule that if I give it an x value, it returns back the y value. So this my domain input, the rule is the line of the function, and my y value is the output. And so this represents set D, or the domain, and this represents set E, or the range. And these are the ways that we will look at functions. And so I guess this is the machine version. This is the arrow diagram. And this is the graph of how we can look at functions. The key to the function is the rule that the function is itself, and how that rule works its way across. Now those rules describe the dependency of one value on another. So let's look at some models that generate function rules. And so your book has some good examples of this here. We can think of a circle. Let me see if I can draw an okay circle here. And the circle has an area. There's some value that represents the space that the circle covers in the xy plane. Now we can calculate the value of that area by using a formula where the area is a function of r. The area depends on the radius. And particularly the rule is pi r squared. And so for each value of r that I put in, I get one value of area coming out of it. And so this is a function with the independent variable r. Independent variable is r. And the dependent variable is a, the area. And so we can say the area depends on the radius of the circle. The function, or the rule, is pi r squared. The domain is, I'm going to exclude 0, right? Because a geometrical object with a radius of 0 isn't a circle. At the best, it's a point. And out to infinity. And so these are all the possible values of r that we can draw from. The range that gets returned is again from 0 to infinity. And this actually tells us some things about the model we're looking at. This says we cannot have a negative radius. And this also says we don't have a negative area. Which makes sense. When we measure until we start dealing with quantities that are vectors and direction matters, a radius is always a positive value. And areas, because they are having a squared term, are definitely always positive values. And so our domain and range tell us something about the model that the function is using. And this function it depends on the input of the radius. And so this is the definitions we're going to be using for a function in this course.